Alright, this is the partner test that I gave you guys yesterday. So, number 1 says that the spinner shown is spun once. Find the probability that you land on a number greater than 3 or black. So we have an OR problem. When there's an OR in the question, we know that we're looking at a mutually exclusive or an inclusive problem. And our equation for mutually exclusive and inclusive was the probability of event A plus the probability of event B, and then we subtract the probability of A and B. So that would be any overlap that happens with the two probabilities. So for this one, we'll say that A is a number greater than 3. So probability of event A for our numbers greater than 3. We have 1, 2, 3, 4, 5 numbers that are greater than 3. And that's out of our 8 numbers total. Our probability of B is the probability of having a black wedge. So we've got 1, 2, 3, 4 black wedges. And that's out of the original 8. Now, do we have wedges that are both greater than 3 and black? Yes, 5 and 7 are black wedges and they're numbers that are greater than 3. So we have to subtract 2 over 8. So then we combine our fractions and we get 7 over 8. And that's as reduced as that fraction gets. So we get 7/8 as our fraction. And then converting that to a percentage, you should get 87.5%. Two and 3 are 2 more examples of inclusive or mutually exclusive. We have to decide which one they are. This time we're told that each of the numbers 1 through 9 is written on a card. The card is placed in a stack and one is drawn at random. For number 2, we want to know the probability that the digit is odd or a multiple of 3. So the digit being odd will be our event A, and the digit being a multiple of 3 will be our event B. For these number ones, I like to write the numbers down so I have them in front of me so I can see what my entire set is. So we have the numbers 1 through 9 is our set. So we need to find the probability of event A. So the probability that the digit is odd. Well, we have 1, 2, 3, 4, 5 odd digits. So 5 out of our 9 are odd. Then we need to add the probability of event B, and that's the probability of being a multiple of 3. Our multiples of 3, we have 1, 2, 3. So we have 3 multiples of 3 out of our 9 numbers. Now, are any of our odd digits also multiples of 3? And the answer is yes. 3 is odd, and 9 is odd. So we have 2 multiples of 3 that are also odd numbers. So we're going to subtract 2 out of 9. We're going to get, when we combine these fractions, we'll get 6 over 9, which reduces to 2/3, because we want to write our fraction as a reduced fraction. And then the percentage we get is 66.7%. Now we needed to decide if this was inclusive or mutually exclusive. We had overlap that we subtracted, so this is an inclusive problem.
Would it matter if I just put 66%?
In the directions it says to do it to the nearest tenth, so you should take it to the nearest tenth, but I would probably take.
Why is it inclusive again?
Because we have an overlap. We have a section where we have odd digits that are also multiples of 3.
Okay.
The two events aren't completely separate. So number 3, now we're looking at the digit is prime or is greater than 7. So A is going to be that the digit is prime. So all of our prime numbers. 1 is not considered a prime number, but 2, 3, 5, and 7 are. So we have 1, 2, 3, 4 prime numbers out of our original 9 numbers. And then we need to add our probability of B, and B is that our number is greater than 7. So we have 8 and 9 are greater than 7, so we have 2 over 9 for the probability of B. Now, are any of our prime numbers also greater than 7? And the answer is no, 8 and 9 are not prime numbers. So we don't have any overlap in this problem, so we don't have to subtract anything. So we'll combine these fractions and we get 6 over 9 again, which again is 2/3. So our reduced fraction is 2/3, and our percentage is again 66.7. Now, this one, our two events were completely separate, so these are mutually exclusive events. Number 4, we have a bag that contains 2 black marbles, 7 white marbles, and 6 green marbles, and 5 blue marbles. An experiment consists of taking 1 marble out of the bag, replacing it, and then selecting another marble. So for part A, we need to determine whether the events are independent or dependent. Remember that independent was if the first event did not affect the second event, and dependent was if the second event depended on what happened in the first event. So reading through the question, we're picking out a marble and we're replacing it. So we're picking out that marble and then we're putting it back. So we end up with the same set as we started with after the first pick. So these are going to be independent events. The second event doesn't matter what happened in the first event. It doesn't take it into account because we're starting out with the set that we started out in the first pick. So we need to find what is the probability of selecting a blue marble and then a green marble. So remember, for independent and dependent, our formula was probability of event A times the probability of event B. So for mutually exclusive and inclusive, we were adding and subtracting. For independent and dependent, we're multiplying. So we need to find the probability of event A, which is, we're going to say, drawing a blue marble. So we have 5 blue marbles to start out with, and that's out of our 20 marbles total, adding up all the marbles in the problem. And then we're going to multiply by the probability of B, which is going to be picking a green marble. We have 6 green marbles, and remember we replaced that first marble that we drew out, so we still have 20 marbles total. Multiplying through, we're going to get 30 over 400, which reduces to 3 over 40. So our reduced fraction is going to be 3 over 40. And our percentage is going to be 7.5%. On the back, number 5 says, Andrew and Jeremy are playing Dwarf with a standard deck of cards. Considering the full deck, what is the probability that Andrew has a red card and Jeremy has a black card? So we have an and problem because we have Andrew with a red card and Jeremy with a black card. So we know that this is going to be either independent or dependent. So we're going to find the probability that Andrew has a red card is event A and Jeremy has a black card is event B. So there are 26 red cards in a deck of cards because half the deck is red, half the deck is black. So we're going to have 26 out of 52 for our probability that Andrew has a red card. And if Andrew has already drawn that red card and we're playing war, we don't put that card back. So Jeremy, there are 26 black cards, but since Andrew already drew the one card, we have one less card. So we have 51 cards in the deck left. When we multiply this through, we're going to get 13 over 51. That's our reduced fraction. And our percentage is 25.5%. Number 6. Consider a drawer that contains 6 black socks, 4 brown socks, and 8 white socks. One sock is taken at random, not replaced, and then another sock is taken. Find each probability. So for part A, we're finding the probability that we pick out a black sock and then a white sock. So these again, we have an AND problem, so we know that these are independent or dependent problems. We're not replacing the first sock that we took out. So we know that these are going to be dependent probabilities. So our probability for event A will be that we find a black, and event B will be drawing a white. So the probability of picking a black sock first, we have 6 black socks out of a total of 18 socks. And then we're going to multiply by the probability of event B, which is picking a white sock. So we have 8 white socks, and we already picked out this black sock, so we have one less sock because we didn't put it back, because these are dependent probabilities. So now we only have 17 socks to pick from for that second sock pick. So multiplying this out, we get 8 over 51. That's our reduced fraction. And our percentage is going to be 15.7%. For part B, we want the probability of picking a white sock and then picking another white sock. And remember, we're not replacing the first sock that we picked. So probability of picking a white sock is 8 out of our original 18 for that first white sock. And then we're multiplying by the probability of picking a white sock again. So we've already picked a white sock. We had 8, so now we only have 7 white socks left to pick from. And again, our total set, because we've already picked one sock and we didn't put it back, we have one less there as well. So we end up with 7 over 17. When we multiply through, we get 28 over 153. And that's the reduced fraction for this one. And our percentage is 18.3%. Number 7. For one roll of a die, let A be event of odd numbers and let B be the event that you roll a 3 or a 4. We need to find each probability as an unreduced fraction. So, when we roll a die, our options for what we could get are numbers 1 through 6. So I like to write them down so I can see them. We have numbers 1 through 6 are our options. So event A, it said that we got an odd number. So for part A, we need to find the probability of that event. So we have 1, 2, 3 odd numbers out of our original 6 total. So our answer for A is 3/6. because remember, you can leave this as an unreduced fraction for this part. Part B wants the probability of event B. Event B was that we rolled a 3 or a 4. Well, we can get a 3 or a 4 one time each, so that's 2 out of our original 6, because you can get a 3 or a 4. So part B is 2 over 6. Now we want the probability of A and B. So the probability that we have an odd number and it's a 3 or a 4. Well, 3 is the only odd number out of 3 or 4. So we have 1 out of 6. So C is 1 out of 6. Part D. Part D is why we found the probability of A, the probability of B, and the probability of A and B. What Part D is asking for is the probability of B given A. So remember, this is conditional probability. Our formula for conditional probability was probability of A and B divided by the probability of A. So we found the probability of A and B was 1 over 6. And we found the probability of A was 3 over 6. So we can plug that complex fraction into our calculators, and you should get 1/3. For number 8, we're going to use the following table, which shows national employment statistics, and we're going to use it to find each of the probabilities as unreduced fractions. So whenever we were given a table, remember I said that it might be helpful to add up your rows and your columns. So our total for this first row is 9,729. Our total for our second row is 9,392. Our total for our first column is 8,937. Our total for our second column is 5,801. And the total for our last column is 4,383. And those totals are just going to make it a little bit easier to find the probabilities in A and B. So part A wants us to find the probability of being male, given that we're a professional. We're in a professional occupation. So remembering that this is again a conditional probability, our formula is probability of male and professional divided by the probability of professional. So that's going to equal, we look for the top number is male and professional, so our number of men that are also in professional occupations is 4,190. So that's our top number, 4,190. Our bottom number is our total number of professionals. So that was the total of this first column, which is 8,937. So 4,190 over 8,937 is our unreduced fraction for that probability. Part B wants the probability of being a laborer given that you're a female. So again, rewriting this using the formula, we have probability of laborer and female divided by the probability of female. So probability of laborer and female, we're gonna look at our women's column and look for our laborers. So this 1432 is the number of women that are also laborers. So 1432 is our top number. And our bottom number is our total number of females, which is the sum of this row, which is the 9,392. And that's the unreduced fraction answer for B. And we're done.